Friday I watched the last bit of the proof, so I'll now indeed observe that it's really easy. So B jump, 1 reduces to A jump. Then we wanted to see from this that B Turing reduces to A, right? This was the half of the theorem which in whose proof I got a little confused. And the way we proved this, or the outline went, was that if B jump 1 reduces to A jump, then from this we can conclude that B and B complement are CE in A, and once we have that B and B complement are CE in A, then I forget what the theorem is called, but there's this standard theorem that says that if a set and its complement are computably enumerable, then the set is computable. And so this is exactly the same thing, computably enumerable using an oracle, then you're computable in that oracle. And so the proof is exactly the same, except that whenever you say Turing machine, you say oracle Turing machine using A as an oracle. So was the other implication of which I think rightly claimed that, of course it's easy, but some of these easy arguments are still allow you to get confused a little bit, and I succeeded in that here. So observation number 1 is that both B and B complement 1 reduce to B jump. Right? If you want to decide whether something is in B, then you can certainly decide this, but you can certainly make up a question that uses B as an oracle that holds exactly when you're in B and that doesn't hold when you're not in B. Namely, the machine you ask is the oracle machine which says, is this number in B? If yes, you hold. If no, you don't hold. Right? And because this gives you a nice, I guess you can make it 1-to-1 by some padding, and you get a nice 1-1 reduction of both B and B complement to B jump, which then, given the problem, 1 reduces to A jump, right? That's our assumption that this happens. So this means that n is in B if and only if f of n is an A jump, right? I just randomly call the composition of these two 1-1 reductions f. Well, but when is f of n in A jump? This happens if right? The machine f of n holds on its own input. Oh, I guess I should be careful. It's the oracle machine f of n which holds on its own input. Well, this happens if and only if. I mean, really, I'm done, right? Being in B is a CE type question, but now it's not really it's not obviously in CE form, so I'll rewrite it so that it is obviously in CE form. We have the universal oracle Turing machine, which does this, right? To be in CE form or CE relative to A, I need a single Turing machine or a single oracle Turing machine using oracle A that holds in the one case and it does not hold in the other case. So that's what I'm working to. Now I essentially have it, except that there's this duplication of inputs, which of course officially our definition of CE doesn't do. So then you just realize that there exists this one machine U prime that as its first action doubles its input on the tape and then starts running U. And so now clearly this N in B is CE relative to A. Oh, I forgot my down arrow. And the exact same thing works for B complement, therefore both of them are C in A. I guess that there isn't really anything going on, but if you do it carefully enough, there is enough steps that you clearly can get lost in it if you apply yourself, like I did on Friday. Good? Everybody happy with that then? Good then. So we have now two classes of sets, possibly relativized to an oracle, which we like, the computable sets and the computably enumerable sets. And we have drawn this picture before, right? Here is 0, here is 0 jump. Well, I guess I didn't call it 0 jump before because I just defined the jump. The 0 degree is the Turing degree of all the computable sets. 0 jump is the degree, the Turing degree of the halting problem, and then we found that all CE sets are in this oval, right? Every computable sets reduces to everything, so in particular reduces to every CE set, and every CE set reduces to the halting problem. So all of the CE sets are in this oval. If you interpret the oval the same way I do, as everything that's in between these two points on there. And so now you could ask, and I'm not going to answer yet, but you could ask, is this oval exactly the CE sets? Well, of course the oval doesn't actually consist of sets, it consists of equivalence classes of sets. It is not the case that every set which is equivalent to a CE set is a CE set, so these degrees contain different kind of sets. But what you could maybe hope for is that every degree in this oval contains a CE set. We certainly don't know that yet, and as a matter of fact, if you know that, then you know something wrong. But right, this is a reasonable question. In order to approach it, we want to enter this at some point. I'm not going to answer it right now, but describe sort of the strategy. In order to approach this, a good start would be to have a characterization of all these sets. Right? If the answer to this question I just described was yes, all of these things are CE sets, then you have a nice characterization. But if you want to go for a no answer, then it's really handy to have a good characterization of the sets in there, or of the degrees in there at least. And so that is the current order of business now. Come up with a good description of these sets.
We do know sort of a converse though that every CE set is somewhere in there, right?
Yes, absolutely. Yeah. Yes, every CE set, even one reduces to the halting problem. So all the CE sets are in there, and therefore it might be really nice if that was all CE sets.
Yeah.
But so we want a characterization. And what do we have? Well, of course we have computable sets, which are really nice. You ask a question, you know it's in there. Then we have the CE sets, which you enumerate. Well, which you enumerate the elements into. You can also think of these things as having a computable sequence of finite sets. So if I give you a computable sequence of finite sets like this, then I can start wondering about the limit of this computable sequence of finite sets, and it's a little bit similar to CE sets. The thing that is different from this general description than it is with CE sets is that for CE sets, this sequence is increasing. Right? The set AS is the number of elements which you have enumerated into the CE set after S steps of computation, something like that. Then you get this really nice increasing sequence which nicely increases towards the CE set. if you have a CE set, then you get this approximation. If you have this approximation which is increasing, then, well, clearly you get from this an enumeration of the corresponding set. So this describes CE sets. And now if we remove the requirement from the A as being increasing, well, then we have a bit of a problem if you don't do anything, because like the limit of AS, what does it mean? Well, you look at the limit of the characteristic functions, they value zeros and ones. And so this limit exists if from some point on every point stabilizes, which a priori is not the case if you just give me a computable sequence of finite sets. You could say, well, 0 is in there in the even stages and it's not in there in the odd stages, and you don't know what happens. So what I want to describe is these things that have a computable sequence of finite sets approximating it, such that this limit exists. These sets that I've then described are called limit computable. And this approximation is then known as a delta 2 approximation. So this is a delta 2 approximation of a set, meaning it is the computable sequence of finite sets such that this limit exists. Then you have a delta 2 approximation. The other approximation, the one where the sets are increasing, is called a sigma 1 approximation, which gives rise to a nice CE set. So in that description of this is a nice generalization of CE sets. In CE sets, what you have is that all points are not in the approximations, and then every now and then you decide to put a point in there. The delta 2 sets have every now and then you put something in there, and then maybe later you change your mind, you take it out again, then you put it back in again, and you take it out again, and you put it back in again. But at some point you need to permanently make up your mind and have it always out or always in. But in the meantime you can fluctuate an arbitrary number of times. And so also in that sense it is a nice generalization of CE sets. If you have such a delta 2 approximation, then there are some functions associated to it. We say mx is a modus of convergence exactly when for every x, for every s greater or equal to m of x, it is the case that a restricted to x is equal to as restricted to x. And you notice that I said restricted, but it is a slightly modified notation for restriction. This is the restriction to x plus 1. I guess plus 1 is like 3 lines, and the harpoon is 1 or 2 depending on how you draw it. So it's a very small safe in notation, but this just means that the est approximation is correct up to and including x plus 1. Now, up to including x, not x plus 1, up to and including x, so x is included here. And not only is it correct, it is, right, from time mx on, it's always correct. So this is not just a correct approximation to the final set, but it is a correct approximation such that this is the approximation for the initial segment that keeps on being the case. Right? Related to that last comment is this incredibly poorly named function of a least modulus function. The least modulus function, incredibly poorly named because it's not necessarily a modulus function, but the least modulus function is the function m sub a of x is the least s such that a restricted to x is equal to as restricted to x. So this is the least point in time where your approximation is correct, but it could be incorrect again at some later point. Now, if we restrict ourselves to CE sets, then that doesn't happen. Right? If you have a correct approximation for a CE set, then all the points that should be in are in, and because in these sigma 1 approximations you never take anything out, so for CE sets, least modulus functions are modulus functions. For other sets, this is the least time when everything looks correct, but then later things might momentarily again look incorrect. Okay. Some nice properties here. Of course, A Turing reduces to its modulus, or to any of its moduli, or to its least modulus function. If you have in M a modulus for a least modulus function, from this you know a time when the approximation is correct. Well, if you know when the approximation is correct and the approximation is computable, then you know what the final value is. Also, the least modulus function, the thing which is not necessarily a modulus function, is computable from A. Right? If you have A and you run your approximation and you go look at AS and then you look at AS plus 1, AS plus 2, AS plus 3, and you can start at 0 and just figure out, well, when is the first time you're correct? If you have A, you know when you're correct, and so you can easily compute when the first time you're correct is. You cannot easily compute when you have stabilized, because there's a halting problem in between. Right? Deciding whether at some point in the future this element is either permanently or temporarily removed from the set is a halting type problem. But the least time when it's correct you can compute from A. If A has a sigma 1 approximation AS, and MA is dominated by G, then reduces to G. And this is very much related to the fact that we're looking at a sigma 1 approximation, because it's definitely false for delta 2 approximations. But in a sigma 1 approximation, if at some point it's correct, it's correct at every point later on, and therefore such a G which dominates. Does everybody know what it means to dominate? Domination means if you're comparing functions, then you're comparing output values, and then the usual star notation, any relation star on the natural numbers means for all but finitely many values. So this means that there exists a case such that for L, all L greater than K, M A of L is less than G of L. But the picture is that here is the one function, then for a little while they can be randomly ordered, but then from some point on the dominating function, right here is K, or the least K that works, from some point on the one function is always above the other function. That means that this function dominates the other one. And so if I have a function which dominates the least modulus function, then for all but finitely many times, this function is greater than m of a. Therefore, for all but these finitely many times, you have a time which you can find from G, at which time you know that the approximation is correct. and so now in this reduction, you just need to do two things. Remember the table of finitely many values where it's not dominating, and above those values you use G to figure out when the approximation is correct. Therefore, A Turing reduces to G. I notice that this one is interesting because it is something, right? If I have M of A, then from it I can definitely compute A, because M of A gives me an exact value when the approximation is correct. In arbitrary delta 2 approximations, G doesn't do that. G is just some point far enough away that before that, at one point or other, the approximation was correct. But it doesn't give you any information about when that point was when you were correct. So this crucially depends on that we have a CE set which is approximated in a sigma 1 way. Right? CE sets also have delta 2 approximations which don't behave so nicely. But
just to be clear, we're using a function as our oracle here?
Yes.
Okay. And then we just find some way of encoding that into the natural number?
Yeah. Just encode it as its graph.
Right.
Maybe.
And you're saying because the sets are increasing, this G is a modus from K on?
Yes. Because this sigma 1 approximation, once it's correct on some segment, it's always correct on some segment. So to then decide this set, all you need is some point of time which is beyond the first time it's correct. And that's exactly what this says. This G is a function which almost always, right, there's finitely many exceptions, but except for those finitely many exceptions, G always gives you a time at which the approximation is correct. Or more appropriate, it always gives you a time past the moment where the approximation first was correct. And then if you have a sigma 1 approximation, the approximation stays correct. Okay, from that then, we can make the observation that, so this is number 4, strangely enough corresponds to the number in my notes. If I have A, sigma 1 approximated by AS, if I have C, sigma 1 approximated by CS, and if MA is dominated by MC, then A Turing reduces to C. Right? Why does this happen? Well, because from C you can compute M of C. Right? If you have a set, you can compute its least modulus from it. Oh, that's item 2. C computes its own least modulus. This least modulus dominates the least modulus of M of A. So, except for finitely many exceptions, which you can encode in your reduction, you can use MC as a time when the approximation to the initial segment of A is correct. So from this you can see that this notion of least modulus is very useful for CE sets, and you can also imagine it being somewhat less optimal for non-CE sets, but for CE sets it gives you a lot of useful information.
What happens finite number of cases where G doesn't dominate in A?
Oh, so it's finitely many cases. So in the Turing machine, in its program, you can remember which these finitely many cases are and what the correct values would be. So this reduction here, for most of the time, this reduction says to decide membership of X in A, compute G of X, compute A of G of S, check whether X is in that one. So this is sort of the usual case. Now it doesn't quite work for these finitely many cases, so the real computation is check whether X is greater than this K. Right? In the Turing machine program, you compare with some K which is big enough to make this work. If you're bigger, then do exactly what I just described. If you're less, then look in a precompiled table of values which are big enough for the approximations and use those in here. You don't seem convinced in the least.
No, I'm just too stupid to get it right now.
No, I would not make such a claim. What does the machine do? The machine on X, this phi on X, checks first of all, do I do this easiest enough? So if X is greater or equal to K, and K is right, one value you need to remember and pick carefully at the beginning of the machine. If it's like this, then the output is X in G of X. This is of course not a function value, it's a proposition, but right, it's either 0 or 1 depending on whether this is true. Maybe I should put like pretend square brackets around something are 0 when it's true and 1 if it's false. No, the other way around, of course.
Just chi sub, which is 1 sub A of G of X, right?
Okay, if you actually want it correct. A sub G of X. Did I get it right now, or is it? I really don't know if there should be a +1 there or not. No, I feel pretty safe about it. Okay, G of X is really close to the right value, and if it's not quite, then this one surely is. In the other case, so if X is less than K, yes, I need my +1 because this is strictly greater than K, right? The way I wrote the definition down here, at K itself, G could still be too low. Oh, but now this function might not be increasing. Maybe I'd rather. No, well, it doesn't matter if it's not increasing, because if your approximation up to X + 1 is correct, then your approximation up to X is also correct. So, you can always use bigger values, because the bigger value says that a larger initial segment is correct. And now your G could claim that it's correct at an earlier time, but it doesn't matter. The initial segment is correct as well. And this is just chi of A of T of X. Right? So in this machine you need to remember what K is and what T is, and T is any time such that up to K the approximation AT is correct.
K +1 maybe.
Sorry?
You could use G of K +1 or something like that.
Oh, absolutely. Yes. So then you really only have to remember the one value K. The one value K determines
The entire initial segment.
exactly how it goes.
But given MA and MC, we can't effectively write that machine. It's just that machine will do it because we don't know what K is.
Oh, absolutely. So but if you want to see this, it's Turing reduced. All you need to show is there exists a machine.
Right.
It is not a matter of, from the earlier information, you can effectively find this machine. But you're absolutely right, you cannot effectively find this machine, because this K can be anything. But given K, this machine does it. And of course, yes, it would be nice. In many of other problems, we wonder, yeah, we can do this, can we do it effectively? Well, here's an example of something we can do. We can't do it effectively, because you can't find K given the input information. But as soon as you have K, this is, I guess you call it like phi of K. For every K there exists one, and for K large enough, it's correct. We good? Beyond this, I'm going to have to write like 5 tuples for a Turing machine. So I'm very hesitant to do. So just think about it. Okay. Some nice definitions. So we have already seen a couple of definitions. Sigma 1 was an existential quantifier over something computable. Pi 1, I forget which definition I gave, but pi 1 is either the complement of sigma 1 or it is a universal quantifier over something computable, which is equivalent. This of course generalizes. Right, the 2 is the one we're now going to use. You already saw me write delta 2, but only in the context of delta 2 approximation. The 2 is what we're using. In general, if you have an n there, what it means is this is an expression of the form there exists for all, there exists with n alternations over R of these values, and this is computable. Right? So the n here describes the number of alterations. The sigma says you start with an existential quantifier, and the 0 is for all of these quantifiers are natural number quantifiers. And so you can see as n increases, you can write down more complicated things. Anything which is sigma n is also sigma n plus 1, because you can just stick in a dummy quantifier and it doesn't do anything. So these sets really are increasing and can express more and more and more.
Is this a statement that's going to be true? If
This is a definition.
I'm sorry, I just don't see A anywhere.
Oh.
That's what I was
Yeah, you guys are so picky today.
yeah, okay.
X is one of the things, yes.
Yeah.
Right. Exactly, thanks. Well, but now this looks horrible, right? X is in there if and only if membership in A is equivalent to an expression of this shape. And we say, well, I guess I can write that very briefly. A is in pi 0 and a complement is in sigma 0 n, and this is exactly the same thing, right? A negation of something computable is computable, and if you take a negation of an expression like this and you push it through using the Morgan's laws, are that what they're called? Right? Existentials become universals and otherwise. And so being pi 0 n means you have this n length alternation of quantifiers, starting with a universal quantifier. And on the inside there is still something computable. Delta 0 n is equal to pi 0 n intersected sigma 0 n. So the delta n sets, in a context like we are in now, where all the quantifiers are going to be natural number quantifiers, it's quite common to leave out the 0 superscript. So delta n sets are ones that can be expressed both as sigma n and as pi n, or equivalently, delta n are those sets that can be expressed as sigma n, and their complements can also be expressed as sigma n. And now we can prove the lemma we were after. I guess now after this definition we can state the lemma and then we'll prove it. The limit lemma says the following are equivalent. Item 1, A is limit computable. A is delta 2, 3, A Turing reduces to 0 jump. Now this shouldn't surprise you very much that 1 and 3 are equivalent, because that's clearly how I introduced it. We were looking for a characterization of all the sets below 0 jump, and now we have it, right? A set is below 0 jump if it has a delta 2 approximation. An approximation that can alternate back and forth a finite unbounded number of times for being in there or not being in there, but eventually the approximation is correct in every value. Well, I think we can finish with this proof. A is limit computable, right? It says there exists this delta 2 approximation. Now, how do you get A? Right, I'm starting to prove. Maybe I should first say what I'm doing. I'm starting to prove 1 implies 2. So I have a delta 2 approximation. I want to show that A can be both expressed as sigma 2 and as pi 2. Right? So A can be expressed, X is in A, if and only if there exists something such that for every something happens. Also, I need to be able to express it by saying, for every there exists something such that something computable happens. Right? And we have a delta 2 approximation, and what do we know about a delta 2 approximation? Eventually it's correct in every value. So saying eventually it's correct in every value can be done in both a pi 2 and a delta 2 way, because you're saying for every value there is a bigger value that gives this output. So that's the one way. And the other way is there exists a value such that for every value bigger I have the correct output. And so both of these things are, the last part is computable. I have the right output. Well, the right output is right. X is in there. If for everything there exists something bigger where the approximation says it's in there, or X is in there if there exists a point such that from then on the approximation always says it's in there. And so it gives the delta 2-ness of the approximation. So then 2 implies 3. 2 implies 3. So what we have now is we have both a pi 2 and a delta 2 way of writing membership in A. So that is to say, we have, for instance, exist as for all t r of x as t, right? This is one of the two expressions we have where r is a computable predicate and s and t are just natural number quantifiers. Now, And we also have a for all there exists expression. So first of all, we notice that this here, right? It is clearly pi1 because it's written as a pi1 expression. Now, what is a pi1 expression or a pi1 set? Right, you're pi1 if you're the complement of a sigma 1 set. Now, sigma 1 sets are reducible to the holding problem. And if you're doing these Turing reductions, and if a set is reducible, so it's its complement. So this set here is computable in the holding problem. Right? Given the oracle of the holding problem, you can decide if it's the case that for every t r of excess t is true. Well, but that's pretty nice, because what do we have then? Well, this whole expression now is sigma s in something which is computable in the holding problem. It's an existential quantification over something which is computable in the holding problem. Therefore, existential over something which is computable is CE. Existential in something which is computable in the holding problem is CE in the holding problem. Now, the quantifier is the other way around. It's very much the same, and you find again that you have this set here, this A, which is CE in the holding problem, and its complement is CE in the holding problem. Now we use this theorem again, whose name I always forget, but that says the generalization of if we have something CE and its complement is CE, then it's computable. These two things now tell you that here we have something which is right, computable in the holding problem, which is to say it's Turing reduces to the holding problem. And we're running really low on time, so I'll be very brief about the last implication. The last implication is from 3 we need to get 1. So if you Turing reduce to the holding problem, then you have a delta 2 approximation. And this is something which I think we are seeing this idea for the first time, but this is, if you do a bit more computability, then this is pretty obvious what to do. Right, we have here that the characteristic function of A is equal to phi e of 0 jump. That is what this says. Right? Now, how can we use this to get a good approximation to A, or a good enough approximation to A? Well, we can just say, I suspect I've never used this notation before. We use this square brackets s at the end of an expression means do everything only for s steps, which is to say, here, okay, we have the holding problem. Well, you can't compute the holding problem, but you can compute the holding problem up to s steps. Do these computations hold in s steps? So that gives you a finite approximation to the holding problem, and then the whole computation you can do only for s steps. And that gives you that here you have a function which clearly cannot converge for anything bigger than s. And therefore we have finite sets that are approximations. Now the question is, yeah, you got approximations, are they any good? Well, are they any good? Yes, they're good enough, because if I don't have this s here, it computes the right value. So in particular, it's a total function. So for every input value, it asks a couple of oracle questions, And for these couple of oracle questions, it needs to have the right answer to compute it. But if I want these 5 oracle questions to be correct, well, 3 of them might be yes, the computation holds. And you just need to have an S which is bigger than the time it takes for these 3 computations to hold for this approximation to be good enough for the particular volume. Now that's a little quick, but I'm out of time. So think about it. If it doesn't become clear by itself from that, ask me on Wednesday.